Hello students, today's session we are going to see about the field due to a uniformly charged thin spherical shell. Previously we have seen the applications of Gauss theorem, this Gauss law. There are three applications are given in your book. First one is field due to a thin long wire, and second one is a field due to a charged sheet, and final one is the field due to a uniformly charged thin spherical shell. In order to find out the electric field, I'm just considering a surface, spherical surface like this. This is a spherical shell in which the charges are placed over it. The charges are placed over it. I'm considering a spherical shell of radius r. This is a spherical shell of radius r. With a uniform surface charge density of sigma. It has a spherical symmetry. Spherical means all the areas are, all the surface will be of symmetrical one. So in order to find out the electric field of the spherical shell, I'm just considering a Gaussian surface outside it. So we can have three separate cases in this one. So we can find electric field outside the shell, that is the field due to the spherical shell at outside of that shell, and second one is on the surface of the shell, and final one is the inside of the shell. First case is at the surface, at the point outside the shell. So this is what the spherical shell. I'm just considering a spherical Gaussian surface in order to find the electric field. This is what the Gaussian surface, and on that surface I'm just considering a point P wherein I'm going to find the electric field. At this point, what is the value of electric field? I'm going to find it out. So if suppose the charges are placed over the surface means the field lines will be emitted radially outwards. So this is what the point P wherein the field will be emitted radially outwards because the charges are placed over it. What is the area vector? Area vector is also act in this direction, and field also acts in this direction. E and area vector both are act in a same direction. So just I'm going to find out the electric field by using the expression. Electric field is electric flux is phi, which is equal to integration of E dot ds is the expression for electric flux. E dot ds means we can write it as E ds cos theta. So this is then theta means what is theta? It is the angle between the field and the area vector. So here field and the area vector both are acting in a same direction. So theta value will become 1. This expression comes out E ds, integration of E ds. So phi is equal to, I'm just taking E as outside. Integrating ds will be integration of ds will be of yes, because integration of dx is x. So phi value is equal to E ds. This is what the expression you will get. So since the surface is sphere, what is the area? We have to replace the surface value. What is the area of the surface? Area of the surface, yes, for the sphere is s is equal to 4 pi r square, and this is the area of sphere. So just this s value can be replaced here. When you replace this, phi is equal to E 4 pi r square. So instead of s, you are replacing 4 pi r square. From the Gauss theorem, we know that phi, which is equal to q pi epsilon naught. Take this as equation 1 and this as equation 2. Equating both the equations. Equating equation 1 and 2, instead of phi, what you can replace? E is equal to, phi, which is equal to E 4 pi r square. Instead of phi value, I'm just replacing this. When you replace this, what you'll get? E is equal to E 4 pi r square is equal to q by epsilon naught. So we want E alone. When you keep the E on the other hand, the rest of the things will go to the right hand side. So q by 4 pi epsilon naught r square. This is what the electric field at the point outside the surface, outside the spherical shell. If the point is considered outside the spherical shell, this is what the expression for the electric field. In other words, we can represent it. That is, we have the surface charge density. Yeah, if the surface is consisting of the charges, means we have the surface charge density. Because how many number of charges are present over the surface, means that is surface charge density. Surface charge density, which is equal to sigma equal to q by s. This is we have studied in the charge configurations. We need q alone. Q means what, you can get the expression sigma as sigma into s, since the surface is sphere. So what you can what the expressions have, instead of s, we can replace, since the surface is a sphere with the radius of r. What is that? This is this radius value we are taking, because of because the surface sphere only we are considering. For that, this r value we are taking. So what else? With the radius of r, q is equal to sigma 4 pi capital R square. So when you replace this expression in this, instead of q value, just replace this one. When you replace this, what you'll get? E is equal to sigma 4 pi capital R squared by, already the expression consisting of 4 pi epsilon naught R square. 4 pi will get cancel each other. E is equal to sigma by epsilon naught capital R squared by R squared. This is another form of electric field, which is when the surface charge density is given. This is literally only the charges. This is charge density. When you are using the charge density, you'll have. So what is the conclusion we can give from the expression? So field is depending upon the r value, that is distance, from the distance of the spherical shell. So why we are taking the distance as from the center? Because when you are considering, when you are looking the expression E is equal to q by 4 pi epsilon naught r square, this is the expression which we are already got in the point charge expression. When you are considering any point charge, the electric field expression you'll get like this. So what the conclusion we can give from this? So whenever the spherical shell consisting of so many charges, means it is we can assume we can consider it as a point charge. All the charges are concentrated towards the center, so we can consider it as a point charge. So this will I'll explain it later. So from this expression, what we can come to the conclusion: if q is greater than 0, E is outwards. If q is less than 0, E is inward. This is what the two conclusions which we have given from the previous expression. So second case is field inside the shell. So previously we have found field outside the shell. Now you have to find the field inside the shell, which is just you are considering, that is assuming this is what the spherical shell which we are considering with the radius of capital R. So inside I'm going to find the field value. So for that, I'm just considering a Gaussian surface inside, with the point is located inside the sphere of radius R. So since the charge enclosed by the Gaussian surface, where the point charges are located outside the charges are located on the surface of the shell, there is no charges are enclosed by this surface. So q will be equal to 0. So E value is equal from this expression. So what is E is equal to q by 4 pi epsilon naught R square. You can replace q as 0. When q becomes 0, the entire expression will become 0. So whenever the charge placed inside, whenever the field inside a spherical shell it does not include any charge, the value will become 0. E value will become 0. So third case, what happens if the charges are, what is the field value on the surface of the shell? What is the value will be of electric field value of at the surface of the shell? Since in this case both the r will have the same, sorry, the point, the radius of the shell is capital R, and the position vector of point P is also a small r. Both the r will be of same. So we know that expression is E is equal to Q by 4 pi epsilon naught R square, or else another expression we have found. So this expression. So in this case, you can replace that value. E is equal to sigma R squared by epsilon naught R square. Since in this case, both the r, small r will be equal to capital R, you can replace small r by capital R. Both will get cancel each other. E will be equal to sigma by epsilon naught. This is an additional case which is I'm giving. Only two cases will be given, has been given in your book. One is field inside and field outside. So just better you can know this. So this is what the electric field value on the surface of the shell. So both the expressions you can have, this expression or this expression, both will you can use. So conclusions. What are the conclusions which we can give for this set of expressions? In case 1, the E value is inversely proportional to the R square. So what is the first case? In this case, E value is inversely proportional to the R square. And the second case, case 2, E is 0 because charge enclosed by the surface, Gaussian surface, is 0. So the electric field value also, sorry, in this case, charge enclosed by the Gaussian surface is 0. So electric field value is also 0. In case 3, it depends on the surface charge density. Sigma is nothing but surface charge density. How much charge is present over it? Just E is directly proportional to the, it depends on sigma value. So electric field due to the uniformly charged shell is 0 at all points inside the cell. Wherever the point you are taking inside the shell, it will be 0. Thank you.